Okay, welcome to CometWatch. We have a very good guest later on in the show. It's Richard Miles, and the last time we talked to Richard was about 10 years ago on CometWatch. And boy, have we got some good stuff for you. So anyway, as always, we'll kick the show off. Oh, John, I forgot to let you introduce yourself.
Hi, how's it going? John Meichner here in the United States.
And also,
Observatory code W62.
and also thanks to Luna Lee for playing us in. Nearly forgot, but I didn't forget. So anyway, as always, here is the British Astronomical Association Comet Section Visual Observations data. This is the shipping forecast. So latest discoveries and news. June 14th, Zhesheng Yang reports a Kreutz Group comet in C2 images.
June 14th, Yango Yoran reports a Kreutz comet in CCOR1 images.
June 15th, discovery of 2026 L2 pan-stars reported.
June 15th, washed up blue cloud reports a Kreutz comet in G1 images.
June the 17th, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
June 17th, Mylar Krasansky reports Kreutz comet in C2 images.
June the 17th, Zhesheng Yang reports a Kreutz Group comet in C2 images.
June 20th, Yang Yu reports a Kreutz comet in CCOR1 images.
June 2021, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
June 22nd, recovery of 2018 VN2 reported by Jean-Francois Souret.
Hang on. All right, okay. June 25th, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
June 26th, recovery of 2021 N1 P/ZTF identified by Maker Meyer.
June 11th. Wow, that's
Yeah,
sequence.
a lot of
June 11th, Michael Stark reports non-group comet in CCOR-1 images.
June 26th, Yang Ru reports a non-group comet in CCR1 images.
June 27th, Django Ruan reports a Kreutz Group comet in C2 images.
June 28th, Michael Stark reports a Kreutz comet in CCOR1 images.
June 29th, recovery of 2021 N1 reported by MPC.
June 29th, recovery of 2006 HR30 reported by CBAT.
June 30th, recovery of 2018 VN2 reported by MPC.
July 1st, Michael Stark reports a Kreutz comet in CCOR1 images.
July the 2nd, Django Ruan reports two Kreutz Group comets in CCOR-1 images.
July 3rd, Michael Stark reports a Kreutz comet in CCOR1 images.
June the 4th, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
July 4th, Rainer Krajcik reports a Marsden comet in C2 images.
July 5th, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
July 8th, recovery of 2005 S2P skiff as 2025 OZ695 reported.
Okay, July 8th, Django Ruan reports a Kreutz Group comet in CCOR-1 images.
July 8th, Eric Branch reports a Kreutz comet in CCOR1 images.
July 9th, Warnchop Boomplod reports a Kreutz Group comet in CCOR-1 images.
July 9th, Jiang Ru reports a Kreutz comet in CCOR1 images.
July the 9th, recovery of 2012 K3 periodic Gibbs reported.
July 12th, Jiang Ru reports a Kreutz comet in CCOR1 images.
And on July the 12th, the update took place. If there's been no recent updates, you can always try the German Comet Group or Seiichi Yoshida's page for information, or the Liga Iberoamericana de Astronomia for observations. That always gets me. Moving on to current comet magnitudes and observable region for 2026 July. So 10P Temple, magnitude 9, bright, 50 degrees north to 85 degrees south, best morning, last visually observed July 2026.
2025 R3 Pan-STARRS, 12th magnitude, trend fading, observability poor elongation, last observed 2026 June.
88P Howell, 12.5, fading, 45 degrees north to 50 degrees south. It's a morning object, last observed June 2026.
Comet 29P Schwassmann-Wachmann, magnitude 13, give or take, varies. Observable from 30 north to 60 south. Visibility in the evening. Last observed 2026 in May.
220P McNaught, 13th magnitude, fade, 40 degrees north to 50 degrees south. It's a morning object, last visually observed June 2026.
Comet 70AP Garrels, magnitude 13.5, steady, poor elongation. Last visually observed on 2026 June.
2023 R1 Pan-STARRS, 13.5, fading, 50 degrees north to 70 degrees south. When visible is the evening, last visually observed 2026 June.
Comet 2024 J3 Atlas, magnitude 14, bright, observability from 50 north to 20 south, visibility all night, not yet observed.
161P Hartley IRAS, 15th magnitude, bright, 5 degrees north to 80 degrees south, morning object, not yet observed.
Comet 169 Neath, magnitude 16, bright, observability from 50 north to 50 south, when visible all night, not yet observed.
And finally, 340 Gale, magnitude double question mark. That's an interesting one. Bright, 45 degrees north to 70 degrees south. It's an evening object, not observed since 1938. Okay, so as always, the details are usually fully updated at the beginning of the month, but some minor updates may still be made more frequently, particularly for brighter comets. The last full update was on July the 21st. The magnitude is a rough value for the mean magnitude reported. Some observers will see the comet brighter than this, others will obviously see it fainter. Unfortunately, it's horses for courses. The observable region is an approximate indication of the latitude at which the comet may be seen by a visual observer. Obviously, under good conditions, comets may be visible outside this range, especially when imaging. And the period when visible is for the UK, if the comet is visible from the UK, otherwise for 30 degrees south or the equator as appropriate. This is obviously the last visual observation as received by the section. Details are often updated on the basis of observations published elsewhere. And obviously, beginners will often find comets fainter than about 7th magnitude difficult to locate. However, on the British Astronomical Association Comet section page, there are links to positions and finder charts. I would suggest you use them. They're very good. In the news, obviously 10P Temple is now reached 10th magnitude. The 44th volume of Comet's Tale, compiled by Nick James, was published mid-February of this year, and contributions for the next issue, possibly out in July, are welcome. Actually, we touched on that in the interview with Richard Miles. Please do submit your observations to COBS, as this ensures that they are correctly formatted and include all the required information. Obviously, Nick James does extract observations from COBS from observers who are affiliated broadly to the BAA group, or are notified that the observations can be used by the BAA. So there is always something you can do as a new observer. Even taking images and submitting them is the best thing to do, as well as submitting them to the Association of Lunar and Planetary Observers Comet section as well, which the BAA does work with on a regular basis. Well, we have an interest, as I said earlier, we do have a fantastic show. We have Richard Miles back, and well, it was, I think, well due, and I will let him take over now. Oh, hang on, I've got to try and stop this recording. Uh,
uh,
Oop.
and
yeah,
I take particular interest in comets and asteroids. Oh,
and of course,
yeah.
we met, I think, at a BAA out of town meeting quite a few years ago. I think it was Bedford School.
Yeah. I went to that one, Bedford School.
Yeah.
That's right. Can you see on my screen, because
Yeah,
I've got the top of my head cut off on my
yeah,
own
you're
computer.
fine.
Oh, good. Yeah, it's just the
So anyway, of course, we started chatting. Of course, we brought up a subject that's pretty much definitely very close to your heart, and always been a interesting one for me. 29p, and it's always the one I have a problem pronouncing. So I cheat and call it SW1, the comet with a London postcode.
yeah. Is
Yeah,
that Kensington? The
something
Royal
like that. Yeah,
Albert. Yeah.
but and of course there's SW2 from the same uh, astronomer, the same pair.
Uh,
And I'm going to get this wrong. I'm sure it's Schwassmann-Wachmann.
oh, that's pretty good. Yeah.
Oh, I got it right for once. But anyway, and of course, the last time we spoke was about 10 years ago.
Yeah.
So I think it's about time that we got you back on the show and to find out what's been going on with 29p SW1. So
Yeah.
take it
So,
away.
yeah. So that's quite pertinent. The fact it was 2016 is essentially the last time I'd published on the subject of 29p in the professional literature. So that was a sort of a three-paper series, blockbuster, if you like, that worked on data that went from 2002 up to 2014. And that data was mainly the Minor Planet Center. And it started when Herbert Rabe sort of wrote his Astrometrica software. And from
Mhm.
2002, which is when it kicked off, people started to observe comets. And they observed the central nucleus, the so-called M2 magnitude. Whereas traditionally, when you quote a magnitude years and years ago, it was mainly the whole comet at the M1 magnitude. So since 2002, this data has been building up at the Minor Planet Center. And in 2007, we had that enormous outburst of 17p Holmes, which was so mind-blowing that it really grabbed my attention big time. And that's what started me on the course. Now, in 2010, by then, I was getting my hands on the use of a large telescopes, the Fawkes telescopes. And I happened on February the 3rd, 2010, to have half an hour with some, on the 2-meter telescope.
Mm.
And I looked to see what had happened. What could I do that's useful? The very day before, 29p had one of its biggest outbursts has been seen. And so 24 hours later, I took these 60-second exposures with a few different filters. And actually that data was in the papers that were published in 2016. So that was how it started. But what happened was we didn't really have good access to the Fawkes telescope, and it was very patchy, and we didn't get that many observations. So in 2014, the BAA and a couple of the observers started to observe, just a few keen amateurs to observe 29p much more intensively. So Kevin Hills was one of the pathfinders on that. He started on that. Mind you, he's given up now, but the other if he ever watches this, maybe you can get back to Kevin, because we've got quite a group of observers we've built up over the years, and the mainstay in terms of who's stayed the course since then has been Jean-François Soulier, And I visited the observatory down in Provence, and that was before he set up what he calls remote 29P. He's actually built an observatory dedicated so that if 29P is visible above the horizon, he'll be observing it.
Yeah.
So that was back in 2014, and the publication was based on the data we had up until then. So there were a few discoveries then, and one of them, the key important one, is that we discovered that the nucleus was actually it looked to be having a different type of outburst that had been missed before, and I called it the mini outburst in the paper.
Mm-hmm.
And the definition of a mini outburst then was a sort of something that was 1 magnitude or less in amplitude. That's a sort of rough idea of how much we call it a mini outburst. But that has, in the 10 years since I published, we've really been getting so much more data. We're getting of the order of 1,000 photometric observations a year. So, and the key thing is we follow it as long as possible. So, just so in case some of the viewers haven't know the details, 29P is trapped in an orbit that's almost circular between the orbit of Jupiter and Saturn. So Jupiter goes around the sun once every 12 years or so, and Saturn goes around every 29 years. Well, 29P goes around every 15 years. So you can see it's trapped closer to Jupiter than to Saturn, and it seems to have been there for certainly over 1,000 years, and looks to have therefore been outbursting, in that position. Now, its circularity as such is quite unlike any other comet in that it doesn't have a parabolic orbit or a very elliptical orbit. Most comets, even Jupiter family comets, have quite an elliptical orbit. But this one has an eccentricity of only 0.04 or so. What that means is that when it's a perihelion, which is about 5.8 AU, it's a certain amount of sunlight intensity. But when it's an aphelion at 6.3 AU, the intensity of the radiation from the sun is only 20% less. So the full range for the comet is 20%. Now, we've discovered a lot more about this comet, and it now looks like it has got itself into a sort of steady state condition. And the outbursts, it gives these outbursts where something like, up to several hundred times, you get an outburst which makes us 100 times brighter than it should be. And that's because a lot of dust has been ejected out into space. So since we published, we've got a system for actually expressing how intense an outburst is. And it's based on the fact that we've been able to measure the actual brightness of the nucleus on its own. Over the years, we've used large telescopes. I won't bore you with how you do it, but we know that it's we call it the absolute magnitude is close on 9.9, 9.8 in the R band. And so if we measure the brightness with a photometric aperture, we're looking at something like 30,000 kilometers, from the nucleus. You're looking at really a large amount of space. So we add up we see the amount of light that's reflected by the nucleus and the extra that's coming off the coma. So when you get an outburst, you can get it. Well, you can get it virtually 1,000, almost 500 times brighter than nucleus potentially. No, I think the brightest actually is 270 times, but those mini outbursts we've been seeing can be as faint as 20.2 of a nucleus. 20% of the area of the nucleus gets thrown out and reflects extra sun, and that's a sort of really weak mini outburst. But one of the discoveries is that these two types are very separate at certain times. So the comet takes 15 years to go around the sun. So everything, there's a season for everything and in its place. And Jupiter, Saturn, and this comet have their seasons. So that just as the Earth does. And what we find is that when it's near aphelion, and it's just going to reach aphelion at the end of September. So what's that? A couple of months. So it's 15 years since it was last at aphelion, and it's just going to arrive there. Well, what we've discovered, and we noted this in the paper that was published, we noticed that around aphelion, the comet seemed to start to outburst in a sort of erratic, periodic way. And we came up with a rotation period, which we thought was the nucleus rotation period. And we have no reason to believe it's not. And that was about 57 days. So one of the really good explanations as to why it does this is that, and we saw this with Comet Holmes, is that anything that rotates extremely slowly has the capacity to build up a crust on the surface. And the reason is that the nighttime periods are very, very long, just like the daytime periods are. So if you've got a 57-day period, your nighttime is nearly a month. And during that month, it gets extremely cold on the dark side, really cold. It's sort of 12, 20 Kelvin. So, certainly it would freeze things like oxygen and nitrogen. And because of that, although there's been a lot of heat absorbed by the nucleus during the 30 days or so that it was in the sunshine, all that heat material gas comes up through the surface. And when it sees the cold, it gets near the surface, it freezes. So once you start to form a crust, you can start to build up a pressure beneath the crust.
Mm-hmm.
And what we published is the idea that below the crust of 29P is a substantial amount of what we call cryomagma.
Yeah.
It's where the gas and the solid held in a certain pressure, you eventually will produce a liquid. And depending on what the composition is, and we know there's a lot of carbon monoxide, for example, it will liquefy. And once you get a liquid, you also get gas dissolved in the liquid. A bit like carbon dioxide dissolving in beer and giving it a head, or in a champagne, so that when you take the cork off the bottom of the champagne, suddenly the pressure is released, and that creates a sudden eruption, essentially, of froth and effervescence. And it's the same really with volcanoes on the Earth. So the analogy with the Earth is really good, because when I talk about two types of outbursts on the comet, there are actually two types of outbursts for volcanoes on the Earth. Obviously, the volcanoes are being driven by molten magma, which is red hot, white hot, and it's molten rock essentially. But because the molten rock is at the bottom of a long pipe in the core of a volcano, when it's not active, there's a plug holding the magma in, and the plug can be several kilometers in height, essentially. So the pressure that holds the molten lava in the volcano can be really high. Now, all you need is a gas that can dissolve in the liquid. So what gas can dissolve in molten lava? Inside the crust of the Earth, when you heat quite a few different types of rocks, they've got water crystallization in them, and the water comes out. So that's quite the common situation. You have to form a crystal, you often have water's part of the crystal structure. So what happens on the Earth is that water dissolves in molten rock at sort of 1200, 1400 degrees C. Like, you wouldn't believe it, but that's what it does deep down below the crust of the Earth. And while that plug is holding the pressure, and while more and more water is dissolving, it's going into solution, it essentially more and more, and it gets more and more saturated with water. Now, if there's an eruption and the plug is suddenly removed, as with the champagne bottle, no longer have you got the head of pressure holding that in, and what you get is an explosive eruption. Mount St. Helens, below a few kilometers of it off. Now, if you didn't get any gas dissolved in it, particularly, not very little at all, you end up with, instead of an explosive volcano, you get an effusive volcano. So Iceland's a classic example. Iceland has had explosive volcanoes in the past, but not in our lifetime and not in really recorded history.
Something like Kilauea as an effusive.
Oh, that's effusive. Yeah, Hawaii is another really good, probably a better example, because it never does. It really never does explode. That mountain of Mauna Kea was built up over tens of millions of years, and it hasn't blown its top off. There's no enormous caldera, as in some other volcanic islands. So anyway, so one of the reasons why we think 29P has these, and when I say has explosive eruptions, we actually know that it only takes an hour or two for the brightness of the nucleus to suddenly go from what it was to its maximum. Now, we've actually observed in the last 10 years about 10 eruptions of 29P from before it actually happens. So someone like Jean-Francois Soulier and Doug Durig in the States have realized that if they keep taking image after image every 60 seconds or so, sooner or later they're going to catch it doing the eruption. And that's what's happening. We've actually got up to 10 now, and this was never done in 2016 or earlier. So we have that data. We know that, for it to build up in brightness in a couple of hours, what happens is the eruption only takes a few minutes. It shuts down after a few minutes, because as the stuff comes out, it takes heat from the magma and it freezes the magma, freezes it back. And then what you've got is a cloud of material. First of all, it starts out just as a small cloud inside the nucleus, if you were looking at it. But after about a few minutes, 5 minutes or so, the cloud is expanding because there's gas pressure blowing it up, just inflating it. And then it starts to get bigger than the nucleus itself. So you can model that sort of gas cloud as it gets bigger. And eventually, after about 20 minutes, it starts to what's called get optically thin. Whereas before 20 minutes, you can't actually see through it. You can't, even if there was a bright star behind it, the light wouldn't get through at all. So after 20 minutes, you start to get a little bit of light coming through. The expansion keeps going. There's no extra material going, but it's accelerating. And then eventually, after a couple of hours, all the particles are far enough away from each other that you can see the stars through the cloud. But each particle is reflecting the sunlight. And when it's a really strong outburst, you'll get 100 times as much light reflected from the outburst coma than you get from a nucleus. So that's a really explosive one. But even the mini outbursts seem to be sudden as well, which is not the case on the Earth. So one explanation is that just like on the Earth, the mini outburst has liquid. You have a crust that cracks, whatever reason, but the liquid, the cryomagma below, hasn't got any gas dissolved in it, really, of and it's not been held under a particularly high pressure. So what it tends to suggest is there's at least two regions on the nucleus. Probably the one that's closer to the equator, it gets more sunlight, is the one that generates the most powerful outburst. But the ones nearer the poles are maybe just effusive, where you get a crack, the material starts coming out, it starts sort of bubbling and you get material ejected, but then it cools itself down and it shuts off. Why there's two types, and they're well separated in terms of what we see. What's happening now is it's approaching aphelion. It's getting to the stage where it's less active because it's getting 20% less heating from the sun. And what we've, in the last 17 months, we've detected 44 outbursts in 17 months, right? Now, they come in two types, strong or very weak. And there's 32 mini outbursts, so they don't get more than about one mag, or we call that we explain the intensity in terms of the equivalent area of the nucleus. So if the outburst cloud was to have reflected exactly the same amount of light as the nucleus, then the magnitude would go up by 3/4. And that would be that the outburst intensity is one nucleus equivalent. So mini outbursts go up to about 4. So then between 4 and 30 nucleus equivalents of intensity, we've only seen one outburst. We had 32 below 4, and we've got one between 4 and 30 in intensity.
Yeah.
It's an enormous gap. And then above 30 up to 165, we've had another 11. And this seems to be a seasonal thing. And the reason back in 2016, when we published and we were able to identify the rotation period, was because it was around aphelion, and only 1/2 of the nucleus was actually giving strong outbursts. And we're in that ballpark now. We're in the same region of its orbit around the sun. So this happened between 2011 and 2013. So we actually weren't able to follow the comet very easily, except to see the strong outbursts. And there was for half its rotation, there was nothing there. So it's doing it again now.
Yeah.
We've had 3 sets with gaps in between, and we're waiting for the next outburst, which is actually due on something, where are they now? In 4 or 5 days' time, the window opens. So in the 10 or 2 weeks after that, the prediction is there'll be a strong outburst, and that will be a 5th repeat. So it's a good time to talk about 29P, because there's a prediction, and we'll see whether it comes true.
And of course, anybody who has access to even remote telescopes can image and provide images for the 29P project. And I know I did that for a while, and then I dropped out for a bit. But and I remember something that you clearly said to me. You said the luminance pictures were the best ones to send.
Yeah,
not full, not RGB.
that's right.
Could you explain for perhaps someone who's listening to our talk for the first time why luminance is better than RGB?
So it comes down to the fact, or the happenstance, that the color of the material of the nucleus, it's a very sort of neutral gray material, but because it's reflecting sunlight, its color essentially is out of sunlight. And so if you measure with a filter, you actually virtually get the same result as you measure without a filter, the luminance situation. And it's a unique thing for this comet particularly, because it doesn't have emission lines. It's not approaching the sun. It's not getting heated. The gas is emitting, lines in the blue and the green. It's just its spectrum is just like the continuous spectrum of the sun, really. And because of that, and because the filter takes out, you lose 70% of the light or more,
Yeah.
much better off, to observe unfiltered or luminance, particularly when it's faint. We can, once it outbursts and it gets bright, there's always somebody, will get filtered images, and we can compare what your results would be with those filtered images. And what we find is there's only a few hundredths of a magnitude difference. So it's a happenstance that makes
Yeah.
life a lot easier. Yeah.
Actually, I think one of the things that really I like about comets and 29P is the Earth science angle, because like you were talking about cryo lava earlier, and I think it's one of the few planetary science is one of the few things where we can take Earth-based observations and apply them quite accurately to solar system objects, to the moons of the outer planets, and to Mars, Venus, and to some degree Pluto. But it's really with comets that the Earth science bit really kicks in, because it having the background. And all right, I'm working off and on my degree. It's going to take a while. I'll
All
probably
right.
finish it in the States.
Well,
Uh,
yeah.
but the thing is, it covers so much um, ground that effectively somebody who has spent most of their time working with volcanoes can switch over to comets, because there is the commonality there.
Yeah, it's a little bit of a shame that the professionals haven't really managed to get onto 29p in a big way, and I need to explain a bit about that. I'll explain by the fact that the BAA has taken up the challenge to observe 29p. We call it Mission 29p for a reason, because there is no space mission going to 29p, which is really a big shortcoming in terms of NASA's choice of missions. And, you need to decide on a mission, because it'll take you a long time, to build the craft and get it there. And a number of universities in the States have applied, have proposals in for space missions. There were two particular ones that were applied around about 2018 or 2020, just before COVID. And because they were rejected, we thought, well, the amateurs need to take the baton and run with it, and actually see, because the main criticism as to why it wasn't accepted was that there wasn't enough information to make it justifiable. We didn't have enough information to show it was any that much more different to an ordinary comet. And what we've got in the last 10 years with Mission 29P is generating that data that actually says, here we've got it's a unique body, but it actually tells us more about solar systems or planetary systems, because we've only got a limited range. But by studying 29p, we could understand some of the exoplanet systems that have there, where you have smaller bodies holding cryomagma beneath
Yeah.
it. So if you start to think of the liquid being aqueous in these other planetary systems, you're then looking at the life. You're looking at a situation where life can be generated, and you don't need a full-blown planet for it to happen. Anyway, coming back to space missions, knowing that they didn't get any probes to go there, they did get time on the James Webb Space Telescope. I think it was February the 20th on 2023, and we knew that time was going to be granted. And so on our website, the BA website, there's one dedicated to Mission 29P, and there's a really complete page, which is looks at James Webb data. So once the observations had been made, within 12 months, the data had to be made available to the general public. So I sort of waited for the professionals to publish before I started, which they did do. But they actually only looked at the most straightforward way of looking at the data. The instruments on James Webb are absolutely spectacular. What they do compared to any other space telescope previous, they're a factor of 100 or more better, depending on what criteria you use. And what it's able to do is to look within a few arcseconds of a nucleus, split that area up into 900 pixels, and in each pixel they carry out something like 900 measurements in 900 different wavelengths. So they have a spectrum for each of those pixels, and you can therefore do all sorts of things with the data. Now, we observed with a 2-meter within hours of James Webb doing so. So we actually were able to calibrate the James Webb images and compare it with ground-based. We made that link using the Mission 29P data. And what we had been thinking about is that we're studying the way in which the coma brightness changes as you go from the nucleus and you go out into space. And what you can do is you can model that intensity curve, and then you can subtract off the coma from the nucleus. So, well, you can do that with the James Webb data. So you can do it for different wavelengths through the spectrum. And the spectrum goes from sort of 0.6 micron all the way up to 5.3. Now, the professionals had only looked at the carbon dioxide and the carbon monoxide signal, which was a very strong emission signal. But when you looked further down into the areas where you got carbon and hydrogen, you started to see little bumps and absorption bands. You see a dirty, great big one as well, which is just the sort of hydrocarbons, an unknown composition. But what I did was I separated the spectrum for the coma and from the spectrum for the nucleus, and that was quite straightforward to do. So then, when you looked at the spectrum of the coma, you saw the emission lines in this 2.3 micron region. When you looked at the same region with the nucleus, you actually had absorption lines where you see carbon monoxide and methane. So you have I'm not sure if I got. So if you had solid methane or solid carbon monoxide on the surface and it reflected sunlight, you'd see these absorption lines, and there they are, visible because you can separate the coma from the nucleus, and I thought that was a really fascinating thing. Now, we were also able to, because the James Webb can see the gas. In the infrared, it measures, and it actually not just sees it, it measures exactly how much gas, in an absolute sense, is in the line of sight at different parts of the. So you can compare the spectrum at, say, 0.6 microns, where the R band is, or 0.7, 0.8. You can measure the amount of dust in the coma. And James Webb has measured the amount of gas for you, because carbon monoxide is the primary gas. It's by far the main constituent. And what we did was to look. You can do a difference ratio between the dust image and the gas image. So you can ratio the dust image to the gas image, and you can you can numerically determine the dust to gas ratio that way. And the marvelous thing about when you do that, especially where you look at where the carbon monoxide is, you find that the dust to gas ratio is at least a factor of 10 lower than you've seen in other comets that we see. So it's a sort of record ultra low dust to gas ratio. What that means is that the gas we're seeing is escaping through the crust. So remember, this isn't an outburst, this is a steady state. Yeah. So during steady state, there's always a residual activity. So you never see it completely inert. So what the dust to gas ratio is telling you is that the gas is squeezing its way through the crust without lifting off the dust with it. So an ordinary comet always, when gas comes through the dust layer, it trains the dust and the dust rises with it, and that's standard practice, and that's how all comets are. But 29P is different. 29P is the gas is coming out without taking the dust with it, and that's a hallmark of a fairly consolidated crust. Obviously, we see that there's some total. So that if you think of the North and the South poles or certain regions, there might, for example, these mini outbursts might all be coming from the North and South Pole region, for example. And the crust might be a different sort of consistency or consolidation in those parts. So if the crust is thicker in the near the equator, and you get a much stronger crust. Now, another thing that we discovered by using the 2-meter telescope is that when the dust comes out, we can measure the speed it comes out at, and it's not that fast. It gets accelerated, but it's only 100 meters per second, right? Well, the escape velocity from the nucleus is 25 meters per second or so, which means that a lot of material falls back onto the nucleus. So the really strong outbursts, a much greater proportion gets chucked out into the solar system. It adds to the zodiacal dust and the zodiacal light. But as you go to the weaker and weaker outbursts, more and more is falling back. So what you're getting over the centuries it's been active, it's been resurfacing itself, right? So each time there's an outburst, you essentially have like black rain fall, and the black and sometimes we actually see that a chunk of material has come out, and then a day later it collides with the nucleus, and there's a sudden drop in brightness. Where's it gone to? It's fallen back on. So if you're putting fresh dust down onto the surface, and then the nighttime comes, and this gas comes out from the nucleus and sees the very cold dust, it condenses and forms an ice, and that causes the dust to the surface tension to pull the dust together. And essentially, what's happening on the nighttime side is reforming. It's actually strengthening, rebuilding the nucleus. And if you imagine layer after layer, like annual tree rings, you gradually build up. And the place that most of it's falling is probably in the equatorial regions. And so that there's a completely different sort of morphology, topology around part of the nucleus compared to the poles, say. So this is all coming out of the observations that a lot of amateurs are making. Typically, we're getting about 30 contributors a year, and we're usually getting about 1,000 observing runs a year. So that's a lot. There's a lot of commitment from the observers. So for 10 years, we've been holding back on publishing. And the reason is we want to cover one full orbit of the sun. We want to cover a full 15 years, really. We used the Minor Planet Center data from 2002 to 2014, but we've only had intensive observations from the beginning of 2014. So this now is the critical time over there's aphelion and a year or two after aphelion. That's when we should see this one half of the nucleus being active with strong outbursts, and the other half not. And the simple explanation on that is that the tilt of the axis, the spin axis of the nucleus, is quite a bit more than the tilt of the Earth's spin axis, which is 23.5 degrees. So if the nucleus is tilted, say, 45, 50 degrees, you then, at different seasons, as it orbits the sun, as it gets to aphelion, what I think is happening is that as more strong outbursts happen, it's changing the spin characteristics of the nucleus. Now, maybe this is maybe the last thing I can leave it with, in terms of understanding why this thing is so peculiar. The outbursts happen because of the heat of the sun. As the crust, the nucleus turns round, and if there's a potential for a cryovolcano and it comes and appears in the morning sun on the morning terminator, gradually, remember during the cold night, it's built up a pressure inside the volcano, call it that. And well, by the time the sun starts beating down on it, that radiation softens the plug, because one of the constituents is hydrocarbon, and that's like a waxy. When it's frozen, it's waxy. So what happens is the strong outbursts are coming from the morning side, right, of the nucleus. Now that's the spin, the rotational kinetic energy is coming around in that one direction, and so as the eruption happens, you get a retro rocket effect, pushing in a certain direction. It's pushing to slow the rotation by definition. Each eruption slows that rotation because it's coming off on the morning terminator, or near there, within say 30, 40 degrees of it. And that keeps slowing the rotation. And the slower that the nucleus rotates, the more likely you can create a liquid, more likely you can create a crust. So it's a self-fulfilling prophecy. It's a process that's reinforcing itself. And this is why, say, 17P, when that outbursts, it seems as though it may have had a rotation period of 44 days because of some Spanish observers picked that up, picked a kick in the activity every 44 days or so. And we've had 12P Pons Brooks, actually, in a couple of years back, has had these types of outbursts. And when we do publish, we'll publish and compare 29P with 12P Pons Brooks, because it looks like 12P Pons Brooks might have a rotation period also, certainly over 10 days. It's another slow rotator. So this is why now it is slowed to 57, and in fact, our initial data at the moment is showing it might have even slowed a touch more and is now 58 days. It might have just. But one of the things I'd like to sort of point out as well is the outburst will affect the tilt of over a long period of time. That retro rocket effect will not just slow, but depending on where it happens, it will may have a tendency to increase the obliquity. What's it called? Is it? Yeah, the tilt angle of the spin axis, and that could mean why we are seeing this at the moment. Half of the rotation, it's not having any strong outbursts, and the other half it is, because the orientation of with the pole pointing towards the Earth and the Sun. So that could be the explanation. It is a consequence of outbursts in the first place. So yeah, it's you can see there's so much coming out of it, and there'll be quite a few papers produced on that subject. It's a completely different alien world compared to comets we know of. It's it, what there was another reason why they were reluctant to send a probe there, and that was the thought that the outburst material would destroy the probe or would deactivate the probe, stop it working. Of course, nowadays, people are boxing much cleverer. And what they do is they realize when you send a probe, you send lots of little probes to go with it that arrive there with the main one. And then they go and do their jobs. And it doesn't matter if one small probe is because you've got 6 or 8 altogether. And they can get and there was a proposal, and I think it's been done for ordinary comets where the probes land and then they can sort of move around the surface, and the Japanese, I think, have been looking at that for asteroids as well, where you can a probe can easily get around the surface if you give it the right mechanics. So
Well,
yeah, I'm hoping that by publishing we'll finally convince the professional community that this object is well worth visiting.
I totally agree with you. Let me just check something. Yeah. Well, the thing is, Rosetta showed us that you can have a main probe visit the object, deploy a small probe, Philae, land on a comet. Oh,
Yeah,
we had some fun with that, yes. We
it
all thought
bounced.
it bounced, but that was good in some respects because it gave the control team a lot more knowledge
Mm.
about how to land in pretty much in a zero G or low G environment. And of course, the other thing is with 29p, we've spent with all the observations, we can time to some degree the outbursts. We know, as you pointed out earlier, we know roughly when there's going to be a major or minor outburst. So you can literally use that information for the mothership to go
Yeah.
close into an orbit, which can either be close in if it's a minor outburst or quiescent, or move off and leave
Mm.
its fleet of little space probes to do the lion's work. And okay, maybe a few of them will get wiped out. Doesn't matter. But that way, you've got a complete system. We did it with Mars. We sent one of the main probes had a lander. It was in orbit. It was the communications hub between the lander and Earth. We did that with Rosetta. And so, yeah, I think 29p, as you point out, would be a brilliant. And of course, ESA has got the Comet interceptor missions approved.
Mm.
I would have thought maybe get the main units up into space at the Lagrange points
Mm.
and use one of the backup probes for a trip to 29p. It won't just it'll also be very useful because it can expand our knowledge of the Jovian system en route. So
Yeah.
you've got a multi-layer mission. You're not just going to visit a comet. You're going to be doing a complete set of science missions all in one go. And I'll be honest, um, this may be a good thing. ESA is very, very good at collaboration missions
Mm.
with the Americans, with the Japanese, with the Russians. We know how to do it. We've done it so often now that everybody gets their share of glory, so to speak. Everybody has a science team involved,
Yes.
specialist. Everybody's got a specialist. They get to look at their data and publish first, and then it becomes available to the public. So, in a lot of respects, going to 29p would be a perfect chance to do pretty much the ultimate comet science. And as you point out, it's a self-healing comet.
Yes. Good way of expressing it. Yeah.
Yeah. So pretty much, you're not going to run out of cometary material for a very long time. Not like comets like Halley or other comets that are coming into the solar system. They get too close to the sun. They lose volatiles. They lose dust. They go back out, and they tend to come back diminished in the future.
Hmm.
But 29P has its nice little orbit with Saturn and Jupiter. It doesn't seem to shed as much mass as the others do. And it also may allow us to understand some of the dark comets that have lost everything and are now technically inert. They're seen as asteroids in a lot of cases,
Yeah.
but every now and again they do the unpredictable. They wake up a little
Yeah.
bit, they give off some dust and grow tails.
But taking your point about Rosetta and the fact that Philae bounced off, all these Jupiter family comets go through what they now call the sort of gateway, which there's a sort of gravitational gateway which is created by the gravity of Jupiter and Saturn. And 29P happens to be resident in that area and has been a long-term resident. But it's a metastable and unstable orbit for all objects that get trapped there, and they won't stay there for necessarily that long. So most of the Jupiter family comets have spent time, they've come closer to the sun but been trapped. So to create, for example, to create a very solid piece of, call it rock, on a comet surface, as happened with Philae, could be evidence that when the nucleus was passing through the gateway region, even millions of years ago, there was some melting and it consolidated the dust and formed a material that is hard, much harder than they expected. So to discover that is, when you think that the raw materials for these comets, they're generally part of the solar nebula. They're not interstellar comets.
Yeah.
They've been formed from condensation of material which formed the planets. So the very distant ones have a very large amount of frozen gas, hypervolatile gas, which those temperatures out there keep it frozen. But as you get in closer than Saturn, things like solid ethane, actually, solid oxygen and solid nitrogen will start to become liquid at certain times, provided there's a way of holding the pressure. And if in the gateway region something can happen, and 29P is sort of an extreme example, it can happen to other comet nuclei, and then they in turn become a Jupiter family comet, and and the rest is history, I suppose.
Well, in some respect, Jupiter is either a friend or a foe, because either it hoovers up dangerous objects hurtling around the solar system, or if it's in a malignant mood, it kicks them into an orbit where it may intercede with us. So in a lot of respects, it's one of those lovely things. It's a love-hate relationship in the solar system.
Yeah, the odds are actually quite evenly stacked, aren't they? They're not so far from sort of equal odds of whether they get it injected closer to the to the sun. They hit Jupiter, or the third option is they get ejected entirely from the solar system. Jupiter's, the gravity of Jupiter is able to do that. Certainly will be ejected to an extremely long parabolic orbit, if a near parabolic orbit. Yeah. So there's lots and lots of reasons why 29P is going to start standing out as the go-to place to visit. And I do think that, with the advances with SpaceX and Starship and that, that although it's difficult to get objects sent to the other side of the solar system quickly, if you can orbit material, so much material so cheaply with Starship, you can afford to actually, a bit like the New Horizons to Pluto, if you propel your probe fast enough, it will get there quite quickly within a few years. And it's just a matter of capturing it and using the gravity of Jupiter to slow it down. So it'd be nice to think that you could have a joint mission where a probe could visit the outer Jovian satellites, or and 29p is part of one launch, so to speak, and that you're having multiple targeting of destinations. Yeah.
And of course, we've got a very good ion drive system that's in use. I believe that was actually it was used to visit some of the minor planets in the inner solar system.
Mm.
It certainly allowed a grand tour of them,
Mm.
and with that technology, getting to Jupiter and getting to 29p will be an awful lot quicker than having to do slingshots around the Earth, Venus,
Yeah.
and the Sun
Yeah.
to get enough momentum and speed to get out to Jupiter.
Yeah. So
So,
maybe it's not all bad that the prospect is on hold at the moment, because just it's a bit like technology, improves with time, and so your launch vehicles can be such that you no longer have to do those slingshots and take years and years. You can see the justification that the extra cost isn't that much greater anymore, and you can just go make a quick mission. Uh, There'll be an incentive after the interceptor mission to be a follow-up for that, and
yeah.
it's the same concept, that so you can sit probes out at the Lagrange point and go from there even.
Well, also with the next series of space stations that I know they're talking about, it's a shame we haven't got Arthur C. Clarke's space wheel, because that would make life so much easier for building stuff. And of course, we could then custom design the space probe in space,
Oh,
um,
right, yeah.
and not have to worry about propelling it through the atmosphere to escape velocity, which is the biggest nightmare. Is how much weight can I have on my space probe, because I've
Yeah.
got to get it from the ground up.
Do you think we might have a time limit on how long we can wait because of the so-called Kessler syndrome? If as it looks, there are going to be many more low Earth orbiting satellites in future, as with the Starlink and so on. They're predicting about over 1 million objects,
Yeah.
satellites, not and and if you start to get a runaway collision, you're going to litter low Earth orbit with a lot of debris. In fact, maybe quite a large area, and it might be that they have to launch everything from through the poles to miss the debris.
Well, yeah, the Earth will have rings like Saturn, but it will just be junk instead of something beautiful made of rock and ice. But as I say, we are
Yeah,
quite a few nations are looking at becoming polar launch facilities. We
right.
have a launch station in Shetland now.
That's right. Yeah.
Um, I believe the Norwegians are interested in that. Certainly, the Canadians are,
Mm.
and of course, the Australians are in the best position possible. Um, we can reactivate Woomera
Oh,
and
yeah.
shoot from
Yeah, but
there.
their latitude isn't quite far enough south, I think. To be,
Well, but
yeah.
it's a lot more convenient for getting stuff up. I think when they were launching Prospero,
Yeah.
it was given the fact that it was a Black Knight rocket, which was actually built for the
Oh, yeah.
military.
Thank you. I'm back now.
Oh gosh, yeah. In fact, the rocket facility on the Isle of Wight is now a tourist attraction.
Oh, yes. Yeah, yeah. I know where you mean it is. Yeah.
Yeah.
It, on the near the Needles, isn't it?
Yeah. Yeah. And you can do tours of the control room and everything
Yeah.
for. So, and I think Australia does have ambitions to get back into the launch game.
Hmm.
That's why ESA has Karuru, is because it's equatorial and it's a lot easier to get to orbit,
Yeah.
and then you can decide where you want to go from there.
Yeah. Yeah.
So,
It's just I said sort of about the window in time because
yeah.
there's some must-do missions, and 29p is one of them. Really, you need to get it off fairly quickly. But yeah, maybe I've never seen any calculations, any serious analysis of how difficult a problem it could become.
Mm.
But I think they sort of don't want to know. It's sort of head in the sand to some extent.
Well, they're all frightened because it's going to be the next big war zone.
Yeah.
People
Well, now
deliberately.
let's keep off that subject.
Yeah, I suppose we really should.
Yeah, you should
But
do. Yeah,
yeah, I think perhaps the Jupiter family, the Centaur family, should be visited because
yeah,
they're a unique environment
yeah,
all of their own,
yeah,
and they
yeah,
have some very good comets which are in extremely good condition,
yeah, yeah.
comparatively speaking, to some of the longer
Pristine.
period.
Yeah. No, I think if you just look at 29p as one of a family, there's lots of members of that family. Chiron, and they're showing low level activity,
Yeah.
and we know that all the comets are getting close to the Earth and pass through that region virtually, and so why it must be from an ion drive rocket point of view, an ideal place to go because the velocities are once you're away from the planet, so really quite low, much lower, and it's easier to hop from one orbit to the next, one AU further out, much more so than sort of in uh, the main asteroid belt.
Well, as I say, ion technology is proven. They're talking about going the next step with it, calling it an impulse drive. I
Oh
think I
yeah,
think I think the eggheads behind that have been watching too much Star Trek, but never
exactly.
mind.
I was going to say that. Yeah, yeah.
It's just one of those things. I've noticed that a lot of people in astrosciences tend to be Star Trek type fans.
No,
They,
yeah.
they 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 were brought up on the next big adventure outside the solar system or
Mm.
inside the solar system through science fiction. Um, so it's really a case of, well, why don't we name stuff after what we've seen on the telly? We can do that. Um, okay, Bill Shatner may pick up a little royalty check out of it. Who knows?
Mm,
I know
mm.
he's been making an awful lot of thing out of the flip phone being from Star Trek.
Oh yeah, yeah,
But yeah, it's one of those things. I think we
yeah.
have a brilliant opportunity to visit comets which are relatively close, astronomically speaking. It really doesn't. You don't have to wait that long for something to come in. So you can have the comet interceptors in place. Okay, we've got to show that they're worth the money. We'll
Mm,
send one off to the
mm.
Centaur group, to the Jupiter family comets. Let them poke around there for a little bit. If they got an ion drive, they could maybe just do two or three comets, have a small lander, two or
Yeah,
three.
they become very cost effective if you start to visit several. And I think of the two proposals, one of them was that sort of thing where you could visit more than one object. There was the other one I think was a flyby, which isn't such a good idea because you're traveling at several kilometers a
Yeah,
second. If you hit the dust, the outburst coma then. Whereas if you put something into a temporary orbit, just like Star Trek does. Um, you don't only have to worry about things coming at you at about 100 meters per second, and they're tiny bits of dust. And if you stay far enough away, the chances are, you won't. And you can build your probe so you have a shield, and
yeah.
you have a shield on one side, and you turn the probe around if there's an outburst. And so it's very easy and it makes it exciting. It's not like a lot of things that once something has been shown on TV or whatever on YouTube, oh, we've seen that before. But with
Yeah.
29p, you really don't know what's going to happen next sometimes. And
And of course, if we catch it, if the mission catches it right, it could actually do science on the way there of a major outburst
yeah,
or a minor outburst, and even as whilst it's traveling, that alone would provide a huge jump in the knowledge that we have.
yeah.
I remember Giotto very well.
Oh yes, yeah,
I was at a certain company in Middlesex.
yeah,
I was invited into the boardroom to watch the big Patrick Moore special from Darmstadt.
that's right.
And the people there were going, as soon as they said the camera's been hit, and it was, oh no, but it didn't matter because we got the pic, we got
It's already been taken.
it had been taken. Yeah, obviously it was a false color image, and
Mm,
that kind of was a negative on the publicity side. Nobody
Yes.
knew what they were looking at
Yeah.
apart from
Well, some
scientists.
amateur astronomers. It's a bit like the moon landing when when the first when Armstrong came down the ladder, he was upside down. He, he- and but yeah, it was. Well, this is it. Don't underestimate how good technology and engineering year on year becomes. The advances that they're making, that what they can equip a probe with nowadays compared even with 20 years ago is so much different. And as time goes on, it's just a matter of getting them up into space and delivering them. And I do hope with SpaceX that they, it's going to be the catalyst, the incentive, because it will make things that much cheaper and it will open the doors to missions that couldn't possibly have been attempted before.
Well, we've got 1960s technology still working on the edge of the
Mm.
solar system.
Yeah, yeah, with the
It's
Voyagers.
transistor logic.
Yeah,
Um,
it's coming up to 50 years.
yeah, and it's still going. It's been through the worst radiation possible at any time in the solar system. It gets caught whenever the sun has a huge fit and blows off. It's made it to the heliopause.
Mm.
It's it's still going strong. I suppose that is really the best thing about our technology. Yes, we've improved it. We've made it lighter. I live just down the road from the Open University.
Mm.
They're fully involved right now in the missions for Europa and stuff. They've been working on the instruments. They've tested all their kit. They know how to look for the. I'm gonna crib this directly from the Sky at Night's latest episode.
Okay.
They have the equipment to see and find the aliens next door. We've had the phosgene emissions on Venus,
Oh yeah, yeah.
which they found when they looked back in the earlier Mariner. I think it was one of the Mariner probes that went there. They
Yeah,
found a reading for phosgene back in that recording. No one
yeah.
bothered to look at it. It was all data in the archive when the universities kicked off with, oh
Mm.
my God, that's phosgene in Venus's atmosphere. Somebody looked back and
Mm.
they found it. So it's nothing new. It's been there and it's just not been found.
Hold on, it happened with oxygen, didn't it? And Halley's Comet,
Yeah,
isn't it? Because oxygen was detected by Rosetta.
yeah,
And in fact, oxygen seems to be present at the few percent level in comets, and it's not possible from the Earth's ground base to have known that. But the Giotto probe to that's right, to Halley did
yeah,
pick it up. Yeah,
yeah. And it went on to Greg Skeller up
yeah.
again. Even without the main camera functioning, it still did positive science. And that is what we should be building on with 29p. We know we can do this. It's just getting the initiative and doing it.
I'm thinking of a good way of ending our conversation, and one of it is that I'm always perplexed that Elon Musk and SpaceX have fixated on the idea of living on Mars and certainly visiting Mars, humans visiting Mars, spending time there, and living on there. And yet, as a scientist, physicist, you know, um, we know that it's such an inhospitable place. You don't, you know, it's so difficult to get to and to get back. And if people die, it's not going to be a good message for the future. And so what instead of putting the efforts into that, the idea of Arthur C. Clarke and the space stations where people can go up and do good work and so on could be a lot more attractive. And okay, I don't see any problem with mining asteroids. That's fine. But I think the cost, and the effort of trying to put humans and sustain a colony on Mars is actually a distraction, and that we have to look for good projects which are going to, grab the imagination of people, and things like, Star Trek, which where people are, are living in space and they're doing
Mm.
missions and they're making things happen and doing science, as well as obtaining, rare elements from asteroids. That can all be done without going to Mars. And let's hope, eventually that's what will happen.
Maybe we need all the astronomers to write to Musk and say, "Look, here's a suggestion for you. You want to make a big mark in history?
Yeah.
Send a mission to 29p." Well, hey, stranger things have happened, and
Uh,
we're saying about Arthur C. Clarke in
yeah.
2001. Every time I hear on the Blue Danube,
Mm, mm.
all I can see in my mind's eye is the Orion spacecraft
Yeah.
going slowly gliding through space, going to the space wheel and
Yeah.
docking. That's that every time that music is played, that's all I ever see.
But I remember seeing Arthur C. Clarke retrospectively at a BAA meeting, and it was he lived in Sri Lanka for most of his later life, but I realised now that the reason he came back to the UK, he was doing I think it was an 11 episode series
Mm.
on strange things. Arthur C. Clarke's Mysterious World, it was called.
Yes, I remember it.
And it was I think it was an 11 or 13, I think it must have been 11 episodes. And I live in Cerne Abbas, and the Cerne Abbas giant was on was one of those episodes. And it was really good. And it was that sort of same year that he came along to a meeting, but didn't make himself known to people
Mm.
at the time. And he really was far-sighted in what he thought
Right.
about. And I do
Yeah.
hope that, that amongst the amateur astronomy community, that there are other people likewise that will be shown to be far-sighted.
Well, his home in Sri Lanka is now almost a museum.
Yeah.
A couple do it is actually privately owned,
Mm,
but you can make arrangements to visit the house.
mm.
They've got all his papers and stuff there, as
Yeah.
all the rooms have been literally left as he left them.
Oh, really? Oh, I didn't know that.
One of the guys I used to work with, where I am now, he's been there, and
Yeah.
he said it is literally left the way it was when he died.
Which is how it should be.
Yeah.
Oh, good.
My abiding memory, you mentioned Apollo 11 and everything. My
Mm.
abiding memory of Apollo was the broadcasting team of Patrick Moore,
Oh, yeah.
Arthur C.
James
Clarke,
Clerk.
and James Burke.
Yeah.
And it's just the way they explained everything. They didn't treat you as if you were an idiot.
Yeah.
They just put everything into simple language. You can
Yeah.
understand.
You and I remember all of that. Um, but I don't think I've seen a recording. I think because most of it was a live transmission, you just soaked it up in real
Yeah.
time for
Yeah.
what it was. It was so special, and people couldn't have recorded back then. They didn't have the ability to make lengthy recordings. They'd have had to have just used a camera to,
I think there is some actually recorded material on YouTube
is
because I go through it every now and again, and
okay. Yeah.
I believe that there is.
Mm,
I will certainly look and put it into the links if I find it.
mm,
But as I say, it was one of those shows. The whole set was simple. It was a U-shaped desk. Patrick at one end, I think it was James at the other, and
mm.
Arthur was in the middle.
Yeah.
And they had some models of the spacecraft and a small moon globe, and that was it. Um, but it worked. It was kind of like the nearest approximation was the guy in From the Earth to the Moon in Tom Hanks's big thing about
Oh,
Mercury, Gemini, and Apollo.
yeah.
The guy who was, I guess he was Walter Cronkite in reality.
Right.
He had a series of models depending on where the mission was.
Yes. Yeah.
And the explanations were kept very, very simple and very low key.
Mm.
And I think that is what's missing today. When we see all these lavish productions for launches, it's a little bit up here sometimes.
Yeah. Yeah.
Um, the graphical information is good. We didn't
Mm.
have that in our day. We couldn't see the actual speed of the rocket. We couldn't see where it was as it was going up into space. We couldn't see it against the atmosphere. We had a little plot that showed where it was for altitude. Um, but I think certainly for us, it was a lot simpler and a lot easier to understand back
Mm.
then. There wasn't an overload of information.
Yeah. But it was a totally unique experience. Yeah. Yeah.
John, anything you want to say?
Oh, I've been listening to you guys. You're really covering the details. The only question I have is, has anybody approached the Chinese about this potential mission?
Good point. I've not heard anything.
Because they're planning a Jovian mission sometime in I think 2029. They're going to be launching, and it's going to be arriving in Jupiter somewhere around 2036 or so. And
Mm.
29P will be fairly close to Jupiter at that point. So I'm just wondering if you could, somehow encourage them to have like a little piggyback probe that can be released to go on its way to 29P. Obviously a flyby, but it's certainly a potential thing they could potentially do, really.
Well, even they could even do a dedicated mission, couldn't they? Because we can't be sure that if you're going to Jupiter, you'll easily get to 29P. But it's too late now. If they're going to launch in 2029,
Right.
um, the hardware and everything will be done. So
Yeah. Yeah,
so
but what about a piggyback approach where you launch the main
yeah.
probe and you launch a little secondary probe? It doesn't have to, as you guys
Uh,
were talking about, electronics and technologies improve. You don't need much of a package as a flyby, essentially. Cameras and some instruments.
yeah, yeah.
CubeSat.
A couple kilograms, essentially.
Yeah, no. The problem is the flyby isn't going to do the business. The
Yeah,
flyby, I know you don't, 29P begs for an orbiter,
yeah,
distant
yeah.
orbiter. So, but you could still do it. We have done occultation observations, stellar occultations, and we know that the shape of the 60-kilometer nucleus is the biggest comet, periodic comet we know of, is quite circular, not perfectly circular, and yeah, so. And by the way, when we published about 12P Pons Brooks, remember the Devil Comet? He had the nickname the Devil Comet because when that expanding outburst coma got bigger and bigger, it overlapped the size of the nucleus and went around expanded beyond the edges. And to create that strange shape, if your nucleus is very close to spherical, that's what you predict would happen. Your hydrodynamic flows would create like an empty cylinder in sort of like a shadow behind the nucleus of the comet, and so the expanding coma would just fill space apart from that empty hollow cylinder. And from the distance of the Earth, that looks like the two horns of the Devil comet. So, 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 so actually, there's a good case for 12P being in hydrostatic equilibrium to produce that spherical shape in the first place. It might have had, cryomagma and a substantial amount of liquid. So, we've got that mission going to Europa, and Europa is very, very spherical because they believe there's an aqueous liquid layer, very thick layer below the ice crust. So let's hope that the Europa Clipper, is it,
Yeah.
will be again another motivation or catalyst, which will make professionals think about going to places where they can find liquids below the surface of a solar system object. So it's all interrelated, isn't it? And John, you made a good point about China, and maybe maybe China is looking for an excuse to do something different, and maybe go one ahead of the rest of the world.
Do
And
you have any contacts in China that are interested in 29P?
yeah, so when you look at amateur astronomers, it turns out there are very, very few indeed active amateurs working in mainland China. Um, You've got some in Taiwan, but in mainland China, there doesn't seem to be a tradition. I don't know quite what it is, but I've looked at the BAA membership figures, it's broken down by country. And the BAA has probably had less than 5 amateurs. Amateurs, this is based in China. There is it Purple Mountain Observatory is one of
Yeah.
the ones. And they do have a nice robotic telescope, and it would, if we could get them to, that would be the first step. Get them to observe 29P because it's at a nice longitude, that's not covered by anywhere else.
Are there any Chinese professional astronomers
Well,
or?
that's a different thing. I think that's where you is the way to go. I think, and the Purple Mountain is a professionally run setup. There's some big telescopes, but to observe 29P, you don't need to use the biggest. And if and by we do have connections with quite a few professionals around the world. Where we got Slovakia's quite active, Ukraine were, but Slovakia's one. We've got a few. We've got a groups.io set up, which we've got 66 members worldwide, and we've got several professionals on that, including Tony Farnham and Laurie Fiega at the University of Maryland. And it would be, as I say, once we start publishing all the data we've got, that's the time when the professionals will really, they will really take note because the data is so comprehensive. We're well over 300 outbursts in the last 12 years, and these are well characterized. So, we're purposely holding off publishing until we've got that full orbit of the sun. And I have got another excuse why I'm not doing that. I'm writing a book at the moment, which I mentioned to Nick, on a different subject, and I need to get that. I need to get that manuscript finished this year, and go from there. So yeah, there's lots. In the next just 2, 3 years, we've got some interesting things. I encourage any observers. One of the observers is Elliot Herman, who's been contributing quite a lot. He's able to use the robotic telescopes in Chile, and he's been a great observer for us in recent years. But there's lots of people: Patrick Wiggins, Andrew Pearce in Australia, um, uh, and Dennis Brzezinski up in north of Scotland. He's been able to do it, but the comet is now moving into the southern hemisphere, and so the ball is very much in the court of our southern hemisphere friends. So yeah, we need to actually actively go out and encourage people to observe. So China should be on our list, I think. And we did get they did attempt to observe an occultation that was passing across that way in 2022, and unfortunately it was cloudy and they weren't able to contribute. But that was picked up in California. Um, so so now it'll be in the southern hemisphere. It will be going through Sagittarius eventually, and there'll be lots of occultations again then.
So
Yeah.
you mentioned that James Webb imaged or observed the comet. Was it they just did spectroscopy, or did they actually actually produce images of the comet that you're
Yeah.
aware
Yeah. So they produce, it's a combination where they produce images within it's basically a 3.3 arcsecond square
of? Okay.
with 900 pixels in. And within each pixel, they had a spectrum for each pixel.
Okay. Do you
So
know when that,
they had everything. But what they couldn't do is the wide field stuff.
yeah. Do you know when that date is going to be released?
Yeah, so as I say, that was released in it was in the summer of 2024, and if you look on the BAA website on Mission 29P, there's a complete dedicated page with the analysis of the data, and it's really quite informative. What I've done is I've held off publishing. I did tell the professionals it was, this exists there on the web. Um, and I just thought that they would do a proper job of the analysis, but take heed of the way that you can do it, the way in which you can separate out the nucleus component. And that hasn't happened. So um, I think what my next task is to write an article for the Comet's Tail. That's the BAA's Comet section. Um, um, Magazine. It comes out 2 or 3 times a year. And I promised Nick James and Dennis that my next job is to do an article. And I'm just waiting for the end of this apparition, which comes to an end in about a month's time. If we'll get a really nice story to include in that. And after that, I think a targeted paper on one particular area of the work. Maybe what I should do is do the targeted paper on the James Webb, actually, because James Webb has got a limited lifetime, I guess, and it would be nice to have good reason for it to be pointed back at 29p. So actually, because I haven't had much response and no one has published, I think I'll write a draft paper and offer to join with, say, the University of Maryland as a co-author, and for people to put their stamp on it. There's 1 or 2 actual universities and colleges in the States which actually were behind the proposal, which was subsequently accepted. So they would also be involved, and we could get something interesting out on that basis. So yeah, this is the advantage of CometWatch, that we have a chat, and
Yeah.
like yourself, John, suggests these ideas, and it gives someone like me the incentive to go ahead and do just that. So it's nice that you've suggested some of these things, and I think, yes, the more I think about it, the more that James Webb data needs to be made more of, and in conjunction with our professional friends. So yeah, I will take that on board later this year.
Good.
I go on, John.
No, that's great. I'm looking forward to it. I wasn't even aware that data was even published, but
Yeah,
I just
yeah,
did a quick look, and yeah, that's certainly interesting. I
yeah.
wasn't aware.
I'm sure we met once at the Big Bear Symposium, one of the ones about 20 years ago. I went to a couple, I think. But did you ever go to Big Bear?
Yeah,
Yeah, you did. I'm sure. Yeah, you did. Yeah.
I was going to say, I think they're going to turn around and say, what did we miss in that James Webb data when they get to see your paper?
Well,
Because
it's not
obviously
my paper. I'm quite happy to do a joint paper. I just don't, I don't want to. It is a joint one with Mission 29P.
yeah,
Like we use
yeah,
the Mission 29P data, and actually the paper that was produced also used and recognized
mm,
Mission 29P. So it's not as though we're not
yeah.
talking and we're not collaborating. It's just that
I
other
wonder,
things become priority
yeah,
for them as well, and so by me doing some of the legwork, it will get something like that off the ground and published, and then there's a slightly more justification for getting another. I think they got about 4 hours time on. I got about getting on for 4 hours time with James Webb.
that's an awful lot of data in
It's a
four
lot,
hours.
eh? Yeah, yeah. They
yeah.
had to integrate for a long time, but it's such a marvelous piece of equipment. It's absolutely astounding, the data. It's so nice to work with.
I
And yeah.
I think, Richard, what we're going to have to do, I'm going to have to make sure we get you back on more often because it's been 10 years, literally 10 years, since we last had you on the show.
Yeah.
And that's way too long. So I think if you're interested, we'll get you to come back, say, end of the year,
Yeah,
and
yeah.
give us a further update on good
Yeah.
old 29p.
Yeah. Well, we'll have had that article in the Comet's Tale magazine, and we can go from there.
Yeah,
Good.
because we've done over an hour and a half just
Yeah,
talking
I
about
think that's long
29p.
enough. Yeah. Yeah.
So I think it's probably, yeah, yes, it's one of those interesting comets. There's a lot more to tell, and yeah, we'll get you back towards the end of the year so we can have some more conversation because I think more is going to be known and more is going to come out certainly by then. So I think at this point, the best thing to say is thank you very much for coming on, Richard. It's been great having you back.
Yeah,
Um,
thank you very much. I really appreciate your time and expertise.
Thank you, John.
well, it's good night from me.
It's good night from him. Good night.
And thank you, Luna Lee, for playing us out.